All right, let's get started. Thanks everybody for coming. I'm going to be talking today about collection data types in LabVIEW. Now, more specifically, I'm going to be talking about strings, arrays, sets, and maps. Now, I'm not much of a terminology guy, but it just so happens that the word collection is already used in LabVIEW. You'll actually see, if you go into the palettes, you'll see a collections palette, and that only includes sets and maps. And so I was trying to come up with a word for what also includes strings and arrays. And so I asked a computer science-minded colleague of mine what term I should use, and he said, "Oh, you should use the term amalgamation." And I said, "No, there is no way I'm using that term. Give me another one." So he gave me a couple more, and I didn't like any of those either. So I decided I'd just settle on the term collection. So if you look in LabVIEW, read the documentation, you'll see the term collection refers to sets and maps, which I will be talking about today. But I'm also going to go ahead and just use it because I want to include strings and arrays as well. Before I get started, I always like to take my presentation content and make it available for anybody. If you go to bit.ly/DNAT collections, there's a page on ni.com where y'all and customers and whoever else can download the slides and the demos, and eventually there will be a link to a recording there as well. Most likely this recording right now. Another thing before we get started, why don't you launch LabVIEW? Play along. If you have LabVIEW on your system, if it is easy, like if you have multiple monitors, or even if you don't, I guess, if it is easy for you to have LabVIEW up and just kind of try the things out that I'm going to be doing in this presentation, go for it. You got to have LabVIEW 2019 or later to do some of the stuff in this presentation. So if you have it, launch it, and we'll play along together as I go through these concepts. First thing I'm going to talk about today is the string data type in LabVIEW. It is one of the fundamental data types in LabVIEW. It's one of the first ones you learn when you learn in our LabVIEW Core 1 class. But I've got a lot of things to say about strings. For one thing, strings are just an array of characters, really. When you really think about it, there is an array of characters, and we are representing that on a LabVIEW front panel, a LabVIEW block diagram, as an array of characters, and those are going to be bytes, so numeric bytes. In LabVIEW, a byte is a U8, and the characters that they represent are mostly characters in the ASCII data set, and I'll talk about that in a minute. But you can see here on this LabVIEW program that I have on the slide, I've got a string. It says DNAT. I've got a function on the block diagram I can use to turn that string into an array of bytes or an array of characters. And just to be sneaky, I threw a space in there after DNAT. So if you actually turn that string into ASCII characters, you'll see the characters and then a space afterwards. So real quick, I want to switch over to LabVIEW to just talk about a few best practices when you're dealing with strings, mainly based on that screenshot that I just showed. So I've got on the diagram here a string constant, and I've got on the diagram another string constant. And those string constants look identical, but they are not identical. If I right-click on this and do /codes display, you'll see that I actually typed a couple of space characters into that string constant. But you couldn't see that just by looking. If I switch this one up here to /codes display, we'll see that it doesn't have anything in it. So one of the best practices I like to do is if I'm on a LabVIEW block diagram and I need to define an empty string, I use the empty string constant. So I use this guy if I want to define an empty string on a block diagram. Now, unfortunately, you cannot drop this guy inside of an array. So you're still kind of stuck with having an array with things that you don't know if they're empty or if they're not. And so one of the things that I like to do to make it a little easier to read a LabVIEW block diagram is most of the time, if I have a string that might contain some white space characters in it, like spaces or carriage returns or whatever, not only will I switch it to /codes display, but I will also choose visible items display style. What that does is that shows a little thing on the left side of the string constant that tells you what the display style currently is. We can see right now it's on /codes. We could switch it over to hex if we want. We could switch it over to normal if we want, and then it looks confusing again because all we see is empty space. So in general, I like to show that display style on a string constant on the block diagram, just so it is easier to know, oh, this is something that has some spaces in it. One time when that can become particularly useful is a lot of the times when you're using the format into string function, you'll have a format string, and you might do something like %s, ABC, %d, blah, blah, blah. And it is useful to know that, oh, wait a minute, if I switch over to slash codes display, we will see that I accidentally typed a space after that %d, and I didn't mean to do that. So when you've got the more complex strings, more complex constants, particularly ones that are being formatted and things like that, it can be a lot easier to sort of discern what's inside of that thing with the slash codes display. So that was just a real quick best practice I wanted to share while I was talking about strings and the fact that you've got these codes in them, the ASCII codes. So remember a couple of those codes because we're going to come back to those. Like, let's just remember on this slide here, capital D in DNAT is character number 68. Let's remember that for a future slide. And that future slide is here. So ASCII, I had to look up what that acronym stood for because I never use the actual words in the acronym. I just say ASCII. But it is basically a mapping of characters to numbers. And if we look at capital D in the ASCII table, we can see that that is number 68. So that's how we get the mappings between the string to byte array in LabVIEW going between characters in a string and numeric values. If you Google ASCII table, you'll get hit with approximately 1 billion results. So just find the table that you like that looks the best and reference that whenever you need to make those mappings.
There's one in the LabVIEW help.
Oh, great. Even better. So what if you need characters to type into LabVIEW that you can't type with your keyboard? There is a tool in Windows called the character map that makes it very easy to grab onto those guys. So for example, if I switch over to LabVIEW again, and on the front panel, let's pretend I know Spanish. I do not, but I know that Inye is a character in Spanish. So what I can do is I can click on it in the character map. I can put it in the characters to copy, put it on my clipboard, and paste it into LabVIEW, and that's how I can get an Inye. I think there's other ways to do it. This is the way I've always done it. It's the easiest way for me. But that is a way that you can grab other characters. Now, the thing is that ASCII table that I showed before, it had 128 total characters in it, mostly English letters, numbers, punctuation marks, several non-printable characters that we don't care about. But that's 2 to the 7th power. So a byte is going to be 8 bits, right? So we can gain access to other characters in the character set on the computer by using that 8th bit whenever we're putting characters, whenever we're basically constructing a character. And like Inye, for example, it's not listed in the ASCII table because it uses that 8th bit to be drawn as a character. Now the problem is that we're just talking about English right now, and I guess Spanish with the Inye. There's a lot of written languages that require way more than what a single byte can provide. A single byte is going to provide 256 characters, right? There's a lot of written languages that need way more than that. And so there are other character sets that can accommodate that. And Unicode is the most common character set that utilizes multiple bytes to accommodate way more characters. And ASCII encoding, just use those 7 bits that I talked about before. UTF-8 is an encoding that utilizes the Unicode character set to provide way more characters. So now we're talking about Asian languages that have thousands of characters. We can accommodate those with something like Unicode. The problem is that LabVIEW does not officially support Unicode. There is a way to get it to support it. I'm not going to talk about that in this presentation, but if you Google LabVIEW Unicode, you can find it. But let me illustrate what that problem looks like in LabVIEW. So if I bring back up my front panel and I bring back up my character map, let's look at a character like this Y with 2 dots on top of it. If we look in the character map, we can see that its byte code is FF. That is the last possible character that can be created with a single byte. And I'm going to put that in my selection. And then if we click on the very next character, which is this A with a line on the top of it, and we put that in our characters to copy, and I try to put that into LabVIEW, then we will see that the Y with the 2 dots on it got pasted just fine, and the A with the line on it did not, because the A with the line on it requires 2 bytes instead of 1. This is what I'm referring to when I say that LabVIEW does not officially support Unicode. Now, if you go Google that and you find the special INI token to add to LabVIEW to use the unofficial support, then if you were to do exactly the same thing I just did and try to paste this character or any of these other characters that are listed in this, way past a single byte, those will all paste correctly. But again, not officially supported by LabVIEW. LabVIEW R&D is looking into ways to better support Unicode in the product. And everything that I've said so far pertains mostly to LabVIEW English. If you're using LabVIEW Japanese, Korean, or Chinese, those will support the Unicode characters without a problem. All that to say, I will not be talking about Unicode anymore in this presentation. I just wanted to give the background because I'm sure somebody was wondering about this. This problem comes up quite a bit. LabVIEW R&D is looking into it. We might have a solution someday. So strings. We just talked about how they could be a set of characters. We just talked about how they could be a set of bytes. When would you want to treat them as a collection of characters? Well, the most common reason is because you have human readable strings, words, phrases, and you want to possibly match patterns in those. There's the match pattern function, the match regular expression function that allow you to detect certain patterns within the string. For example, the one that's shown on the slide here, that pattern with the match pattern function will detect any number in a string, including negative numbers and including decimal numbers. So pretty useful if you're using match pattern, right? If your string was an array of bytes, you could still write code that would detect the bytes that represent a number, like a character number, but it would be a lot harder than what you see here. Also, if you have a string that needs to drive a case structure, that's another reason when using a string as a collection of characters is useful. You cannot wire an array of bytes into the selector for a case structure. So this is another reason you want to use a string. When would you want to treat a string as a collection of bytes? The array functions in LabVIEW can be much more performant than the string parsing functions in some situations. So if you're going for performance, I've seen coding challenges in LabVIEW before where there was string parsing that had to be done. And a lot of the times, the best solutions were the ones that at the very beginning turned the string into an array of bytes and then just processed it as an array of as opposed to processing it as a string. There's way more array functions available for sort of, micromanaging the contents of the array than the string. I'm actually going to have a slide later that shows those. Also, arrays can be operated on in place. I'm not going to talk about in placeness in this presentation, but there is, if you never heard the term before, go check out that link that's in the slides. LabVIEW compiler under the hood has a huge section about the concept of in placeness, which basically means LabVIEW's ability to reuse portions of memory to improve performance. Another reason you might want to treat a string as a collection of bytes is because it should have been a collection of bytes in the first place. The example that I like to give is the TCP functions in LabVIEW. The TCP read is going to give you back a string. Almost always, that is an array of bytes that you want to process. The fact that it comes back as a string kind of adds an extra step that you now have to go turn it into the array of bytes that you want to do stuff with. So that's kind of the intro to strings. There are several examples that ship with LabVIEW that talk about some of these concepts, including the pattern on the previous slide that will match any number inside of a string. That's in one of those examples. I have copy pasted that pattern out of that example more times than I like to admit. So there's some pretty useful stuff in those examples to learn more about strings and to work with strings. So I'm going to go ahead and move on now to talk about arrays. All right, another fundamental data type in LabVIEW, a way to collect multiple elements of any data type, and you can have 1D, 2D, 3D, and more dimensions. All the elements of the array must be the same data type, and if you need to access an element of the array, you always access it by its index. Now, the first question that I always hear when someone's first learning about arrays is when you put that little parenthetical up there in the sentence. Why can't I have an array of arrays? I don't know. I didn't write LabVIEW 1.0, but apparently they didn't do it for some reason. But we can almost get you there with a little trick, which is to take an array, stick a cluster inside of it. The only thing in that cluster is an array. Now you effectively have an array of arrays, just with that extra layer of cluster inside of it. So if you've ever heard the phrase jagged array, that's what this is talking about. It's the closest thing you can have to an array of arrays in LabVIEW. I'm often surprised at the number of people that don't know about this little trick. So even though it's not really pertinent to the rest of this section, I wanted to mention it here because it's a pretty nifty trick if you ever need that. And I pretty often need to do this for various LabVIEW applications that I work on. So my goodness, when I got into LabVIEW, I came from an engineering background. I did not come from a computer science background, and the zero index thing about arrays always kind of threw me a little bit. I'm used to it now, of course, except for the occasion like last week, actually, I was working with a customer who was dealing with a piece of hardware where they had named the channels 1 through 24. And so they referenced everything in their documentation, in their requirements, in their user interfaces in LabVIEW to indexing the channels 1 through 24. And that channel data, of course, was an array of 24 values. But if you ever need to index channel 6, you actually need to pull out channel element 5 from the array. So the code was just full of increments and decrements everywhere, where they were converting from this UI of 1-based indices to the LabVIEW block diagram of 0-based indices. So I kind of wished from the beginning they had referred to them as channels 0 through 23 instead of channels 1 through 24. But this thing bites us way more often than it should, and it's something we always have to keep in mind. You have a for loop, you wire a 10 into its in, but the very last iteration count is going to be 9. So it's always something that we need to keep an eye out for, as evidenced by this slide. I want to pull out the 6th element from the array. Oh, I have to put in index 5 to get it. So keep an eye out for that. It can be tricky. It can cause you trouble if you're not looking out for it. So remember before I mentioned the number of array manipulation functions available in LabVIEW? Here's most of them, and there's way more that I didn't even put on the slide. But all sorts of things allowing you to manage, putting things in the array, taking things out, grabbing a piece of the array, sorting the array, reversing the order of the array, all sorts of these things you can do with arrays. So again, when you're having to sort of massage the data a lot, if your data is a string that really should be an array of bytes, this might be one of the reasons, because of all the different ways you might need to massage that data. Now, some of you may have never heard of the matrix data type in LabVIEW. It is kind of obscure. However, there is a whole palette of matrix functions in LabVIEW that use the matrix data type. You can see that it kind of looks like a 2D array, right? Well, that's because it is a 2D array. It's a 2D array of doubles. You can also have complex doubles if you're dealing with, imaginary numbers. But it can be a little confusing because you're used to seeing that double-lined wire, for a 2D array, and now you've got this chain-looking wire, and you're thinking, wait a minute, LabVIEW class wires kind of look like a chain. Is that thing a class? No, it's just a 2D array. LabVIEW draws the wire special. Any function that can take a 2D array of doubles can take a matrix, and any function that can take a matrix can take a 2D array of doubles. So just that. It feels like we kind of overcomplicated things by adding this other data type that behaves almost exactly like another one. But I just wanted to mention that if you ever run across a matrix, you wonder, what the heck is that? Just a 2D array of doubles. That's all you really need to know. So here are some tricks that might prove useful. Hopefully some of these are new to you guys. It is very often required to get the last element out of an array. And most of the time you might think, well, let me get the array size. Let me subtract 1 because arrays are 0 index and use the index array function. That would be the straightforward way to do it. The easy way to do it is just delete from array. So you drop the delete from array function. By default, it deletes the last element of the array if you don't wire anything in. And so you don't even use the array output from it. You just use this to grab the last element and keep on going with your stuff. Right below that, we have the matrix size function. So I just talked about matrices. This is kind of one of the reasons I did. When you hear the name matrix size, you assume that means you have to wire a matrix into that function. Not true. You can wire any 2D array into that function to get the number of rows and the number of columns. So that's another quick little trick there. In the upper right, I have seen way too much code where people think they have to wire every single index input on the index array function. And there are some shortcuts to where you can't. Look at what my code looks like there. I did not wire the first index of index array. So by default, that's going to pull out element 0. The next one is going to pull out element number 1. Then I said, hey, I want element number 5. Then the next one I didn't wire. So it goes to the next element and says, hey, I'll give you element number 6. Then the next one I did wire to element 9. So you only need to wire indices for where you want to start pulling out elements. And if you want to start pulling out elements at element 0, you don't have to wire anything at all. So hopefully that'll save you guys some wiring time. Then there in the middle of the slide, If you haven't used LabVIEW in a while, or if you're used to using some old versions of LabVIEW, you may not be aware of lots of new functions that have been added to the language in general. There's just new functions everywhere in LabVIEW. But in particular, there's some really cool array functions that you may not be aware of. Stuff like randomize an array with the shuffle 1D array function, remove duplicates from an array, sort a 2D array based on a column. All of those things are in there now. So take a look. If you haven't looked at the array functions in LabVIEW in a while, you might find some pretty useful stuff. And then finally, the in-place element structure over on the far right there. That function has been in LabVIEW since version, I don't remember. It's been around for a long, long time now. And it allows you to operate on elements in an array in place. Now, again, I'm not going to talk about in-placeness in this presentation, just safe to assume it is a way to operate on data more efficiently in LabVIEW. But in addition to performance-wise, if you use the in-place element structure, it actually saves you on wiring as well. Because if you did not have the in-place element structure for the code that you see on the block diagram there, you would have an index array on the left, a replace array element on the right. You'd have an array wire going over, you'd have an index wire going over, and using in-place element structure just saves you some space on your block diagram. Thanks, Norm, for your comments about split 1D array. That's a good function as well. All right, so there are several array examples that ship with LabVIEW. Again, go browse those examples if you haven't seen them before. They introduce a lot of the concepts. Build array is talked about in some of those examples. I didn't really talk about build array here, but it's probably the most common used array function in LabVIEW. So here's the thing about arrays. They have a lot of uses in LabVIEW, which makes sense. We've had them around for forever. If you have data that you need to look up based on index, using an array makes a lot of sense. And one of the most common things you might need to do is if you have a user interface where people are picking something in a list, right? I've got a list box on my front panel, or maybe I've got a ring, a drop-down ring, and there's, 10 things in there. And on my block diagram, I've got an array of 10 things corresponding to whatever you picked on the front panel. That makes sense. You click in the list box, you get the list box value, and you pull out whatever element from that array you need. Arrays make a lot of sense for that, all right? So other reasons you might need to use arrays. If you need to keep duplicates in your array for whatever reason, that's a data type that allows you to store duplicate elements. If it isn't required that your elements be sorted, that's another reason you might want to use an array. There's a ton of APIs already in LabVIEW that require arrays. Like if you look at mean.vi as the simplest example, you got to wire an array of numbers into that to take the average, right? Obviously, you got to use an array there. If you need 2, 3, 4 dimensions on your array, hopefully you don't need 4 dimensions, but if you need 2 or 3 dimensions on your array, you got to use the array data type. And then, of course, if you're in LabVIEW 2018 or earlier, array is pretty much your only option. But if you are in LabVIEW 2019 or later, you have a new option, which is the set data type, which I'm guessing is one of the reasons most of y'all are attending today, is because you want to learn about these new data types in LabVIEW. Well, I had to set the background, you see, guys. I had to set the background for sets and maps by talking about strings and arrays. So the set data type was introduced in LabVIEW 2019, and it is very similar to a 1D array. For one thing, it has a single data type in it. The set that I'm showing on the slide here is a set of doubles. So that's just the data type that's stored in the set. And it's a way to collect multiple elements, right? Just like an array is. But there are several differences too. With a set, there is no such thing as an index-based lookup. You cannot look up something in a set based on its index in the set. There's no concept of an index. An array, that's the only way you can look things up is by their index. With a set, you can't. Also, you cannot store duplicate elements in a set. If you look at the example on the slide there, we took an array, it had several duplicates in it, but the resulting set did not have any duplicates. And the data is stored sorted, as you can see, which makes an insert for a set, it can be slower than an insert for an array because the set is kept sorted when you put new data values into it. And the set can contain any data type. Now, I said that about arrays, right? Arrays can contain any data type. Well, an array cannot contain an array, but a set can contain a set. So I've never had to do this, but if for whatever reason you need a set of sets, that is possible, because when I say a set can contain any data type, I mean it can contain any data type. So before I move on in the slides, I'm going to do a little demo about kind of a use case for sets. all right? And I'm going to write live LabVIEW code, so I apologize with whatever I mess up here. But I'm going to write some code that does a spell check of a string, okay? And the first thing I'm going to do is I'm going to read in a dictionary file. Now, y'all may be wondering, where am I getting a dictionary file? Well, pay close attention, because if you have the VI Analyzer Toolkit installed, then you have a dictionary file on your computer. It is right here. So I'm going to read in this dictionary file, and it's going to come back as an array of lines. And I'm going to convert that array of lines into a set. So insert into set is the function I'm going to use. I'm going to take that array of lines, turn it into a set. I don't like to create set constants on the block diagram. They're kind of tedious. Like, you can create a set constant from the palettes or from QuickDrop, but instead I just do it this way, where I just make the wire in the data type for my set, and then I just create the constant from the shift register. So if I run this code, we should see that it creates a set with all of the words in the dictionary from A to Zimmergy. So I don't want to read this text file every time. So why don't I just create a constant from that set? Then I can get rid of all this code. Now I've got a set constant with all of the letters, all of the words from the dictionary. And I'm going to make a string on my front panel that is going to be the sentence that I'm going to spell check. And I'm going to say this sentence has no spelling errors, because it doesn't. And I'm going to turn it lowercase, because all the words in my dictionary are lowercase. And then what I'm going to do is turn that sentence into an array of words. So how about we take the delimited string based on space characters and turn that into an array of words. So now I should have an array of all the words in my sentence. And then all I'm going to use is the function element of set. So for each string, I'm going to see, are you an element of this set of dictionary words? And if you are not, I'm going to add you to my list of spelling errors. By the way, you might notice I like the NXG controls on the front panel. I think they look cooler than the basic modern controls, so I use them as my default style. All right, so now if we run this code, we don't have any spelling errors. Now let's throw some W's into my words, and we see that it detected the spelling errors. So I could have used an array for all of this, right? I could have had an array of all of my words. I could have used the search 1D array function. And shoot, I could have even used the search sorted 1D array function, which is in newer versions of LabVIEW, because I know that this is sorted. But the lookup for search 1D array is going to be linear. The lookup for search sorted array is probably going to be similar to the lookup for set. But this way, with using a set, I know things are sorted. I know there's no duplicates. And the set data type just makes more sense for this type of operation than the array data type.
Hey, Darren,
Yes,
I'll wait for questions or throw them out at you.
go for it.
When it comes down to the amount of horsepower to turn said things into sets, has anybody that you know of done any effort to figure out, like, oh yeah, you got to be careful, because when you go from large thing into a set in order to perform the operation that you're talking about, it's actually worse than if you just would have done the linear search and gone from there.
Right, that's thanks, Norm. So when we talk about sets and maps, I'll be talking about maps later, we are almost always really focused on the lookup performance. So if you are concerned about how much time it takes you to build up the data set that you're going to be looking at, whether you choose to build an array or choose to build up a set, sets and maps are not optimized for the building of the set and the map. I mean, you know, they obviously R&D did whatever they could to make it as fast as possible. But for example, let's say I did want to work on this set as an array. So I took the set, by the way, this is a little trick you can do. I'll show this in the slides later. But you can actually wire a set to the border of a for loop and use that to index out the elements of the set, and then you can turn them into an array. So this code right here builds up an array of the items that are in the set. This code right here takes a long time. Not a long time. Like if I run the code, it doesn't take a long time. But operating on each element in a set or in a map is not something you want to do in a performance-intensive situation. If you are really concerned about data lookup time, that is when you want to figure out how you can optimize getting the data into set or map form so that the lookups are as fast as possible. Does that help, Norm?
Yes. Yeah.
Great. All right. So what are some common things that we do with sets? Well, y'all saw when I just did that demo, when I pulled the words out of the dictionary file, I used the insert into set function to put them all into a set. There is the collection size function, which is basically like the array size function, but for a set. Then there is the function I used in my spell checker. Is this word an element of my dictionary set? And it returns a Boolean if it's found or not. Then if you need to remove elements from your set, we've got the function for that. And then as I described when I was answering Norm's question, you can iterate over every element in a set simply by wiring the set to the border of a for loop. So yeah, those are the common operations you can do with sets. Here are some not as common operations you can do with sets. You can build a set from scratch using scalar elements on the block diagram. You can see I'm using the build set function to build a couple of sets of path values. I wouldn't say I never use this function, but I don't use it very often. My sets usually I'm either creating from scratch from 0 elements, or I'm starting off with a data set that I'm converting to a set like I did in the dictionary example that I just showed. And then, let's take us back to our high school and college logic classes. We can do things like the union and the intersection and the difference on our sets if we need to for whatever reason. Maybe certain coding challenges might utilize those functions. I'm not sure. I'll move on here. All right, so there is a shipping example in LabVIEW that illustrates how to work with sets, and you can grab it in the examples collections folder. So to recap when sets are useful, first of all, you got to be in LabVIEW 2019 or later. Next, if you do not ever need to look things up based on index, if your need is, I need to know whether or not this element is in this set, that is when you use sets. If you want fast queries, you want to go with a set. And if you don't care about slow inserts, because adding elements to the end of an array, it's just faster than adding elements to a set because the array doesn't have to be sorted and the set is kept sorted. Now, again, LabVIEW tries to be as efficient as possible when adding elements to a set. But if you're trying to optimize the generation of your collection, you might want to go with array instead of set if you don't care about sorting and if you don't care about duplicates. But the query is way faster on a set than it is on an array, especially if it's a linear regular search 1D array. If you don't want duplicate elements and like you want to prevent duplicate elements, then sets are good. If you don't need any sort of associated data, like key value pairs, which I'm going to talk about next. And then if you need fast random element access, so there's a lot of times where you need to just pull a random element out of an array, right? Well, look at this code here. The code on the top pulls a random element out of an array. And if you're not aware, LabVIEW has the random number range function where you give it a range of numbers and it'll generate a random value. If you want a random element out of an array, you just generate a random number and pull out the element at that index, and you're good. That's very efficient. Pulling out a random element from a set is not efficient. Look at that code there. I basically get the size of the set, and I tell the for loop that's iterating over the set, iterate a random number of times and give me whatever the last element was once you're done iterating. So if an array has 1 million elements and you want to pull out element number 1 million, the code at the top runs just as fast as if you want to pull out element number 0. The code on the bottom, if you end up pulling out the millionth element out of a set, that means you iterated over every single element of the set before you found the random one you wanted. So these are some of the ways your brain has to switch and think a little bit differently when you're working with sets than when you're working with maps. Norm, did you have a question?
Did. It was a bit of a wanting to go back a slide and just reiterate something because it took me a long time to really see the value of sets, and I think this is going to help lock something into people's brains as well. Oh, I guess, yeah, this one right here. This is the other one that really jumps out because the points that you're making of like, when would you want to use a set? You're talking a lot of like, well, it's just a collection and it's just you're looking for a thing. That comparison and that difference in the intersections of complete sets, I think that's probably the maybe the more powerful one, especially with the upcoming things that might be happening, where you really have to say, like, basically, if you're looking for a path and you have multiple paths and you want to see if certain like nodes will cross, and I have a path that's made up of a bunch of points and another path that's made up of a bunch of points, and I guess thinking about sets in terms of a database where it's the Venn diagram of things, that's when my mind really opened up and I really started thinking about sets more appropriately, because before that it was just focusing on, okay, it's just like an array, but it has a little bit more and a little bit less, but it's these things, the union and the intersection, that's the big difference for me, that locked it in.
Thanks, Norm. Yeah, I appreciate you contributing that. You can unraise your hand now. But yeah, that's I am not as algorithmically minded as Norm is, so I appreciated that he contributed that because that's an excellent point. Okay, so with that, I'm going to switch over and talk about maps now. So maps were also introduced in LabVIEW 2019 along with sets. Maps and sets make up the collections palette in LabVIEW. If you go into LabVIEW, which I'm about to do, and bring up the palettes, which I never do, you will see the collections palette has maps and sets. So this is where you find that stuff. In all my demos before, I was just using quick drop, so you never saw where they were. But the palettes, I can admit, are useful when you're trying to become familiar with a new API. So in this case, taking a look at the map palette and the set palette, those are the new collection data types in LabVIEW 2019 and later. But a map is a way to store data as a key value pair. So you can see that the wire appearance of a map, it's similar to the wire appearance of a set. They have that snaky look to them. But a map stores pairs of data as opposed to individual elements of data like a set does. So here in this map, what I've got is my key, again, which can be any data type, is a numeric that represents an account number. Let's say this is for a bank. So I've got an account number. Then the value is basically all of the information associated with that account: first name, last name, login, and balance. So we can see that I took, basically, there is no way to have multiple keys that are the same value. So this is a very easy way to create a lookup table where we guarantee unique keys, and then each key can have any value associated with it. Again, maps are like sets in that you can use any data type. Any LabVIEW data type can be your key. Any LabVIEW data type can be your value. So if we look at some common things you might do with a map, this block diagram looks very similar to the block diagram I showed for sets earlier. We have a function that allows us to insert items into a map. So you can have a key value pair. And in this case, my map is very simple. My key is a string and my value is a numeric. So I insert those pairs. I can check to see what the size of my map is, how many elements are in the map. I can look to see if there is an element in my map and return the value associated with it. So if we look at the code on the previous slide, we can see that I wired in an account number to look in map, so I could pull back the value associated with that key. And then you can remove elements from your map. And then just like with sets, you can also iterate on every value inside of the map with a for loop. But there's one extra step. Since the map is a key value pair, that means you need an unbundle function to unbundle the key and the value inside the for loop, and then you can convert those into an array. A couple of things that aren't as common with maps is, again, building a map from scratch on a block diagram. I don't think I have ever done that, but it's certainly possible. And then if you need to go in and edit a certain element of the map, you can go in and basically look it up with the in-place element structure, modify its value, and then stick it back into the map. There are several examples that ship with LabVIEW pertaining to maps. You can grab them in the examples collections folder. Now there are, so far I have encountered at least 3 gotchas with maps that I would like to share with everybody. The first one is the most infuriating. If you check for elements of set, there is a Boolean that comes out that tells you if the element was found. If you check if a key is in your map, yep, there is a Boolean that comes out that tells you if your key is not found. So this bothers me to no end. Before I wrote this presentation, I asked the developer in LabVIEW R&D who is responsible for sets and maps. I said, dude, come on, why are they the opposite? And his response to me was that he did an analysis of use cases for sets and use cases for maps. And the most common thing you would be checking for if using these 2 functions with sets and maps. And his conclusion was that most of the time when you're checking if something is in an element of set, you want to do something if it is found. And his conclusion was, most of the time when you are checking to see if something is in a map, you want to do something if the element is not found. And immediately after he told me both of those things, he said, I might have been wrong about all of that. So it's too late to change it now, but that is definitely something you got to look out for, is that those 2 functions have inverted logic, and you need to, basically my idea is, or my general practice is, whenever I use element of set or look in map, I always hover over it with my mouse and look at the context help to remind me which way it operates, found or not found. All right, the next gotcha is there was a bug in LabVIEW where if you used certain types of references as your keys for your maps, the lookups would go wrong. And that bug was supposedly fixed in 2020 SP1 F1, but I'm still a little scared. So I usually try to find something other than a reference type to use as my key. As you can see my example in the slide here. If I want to use a control as a key, which is pretty common, a lot of the times you'll have a front panel in LabVIEW and you've got data on the block diagram associated with each of those controls. That's a perfect use case for a map. Your key is going to be the control and your value is going to be whatever data that is. I like to just use the label on the control as a string-based key because I'm still a little bit scared to use references. And I have a customer who I worked with, and I changed some of his map lookups to do exactly what you see in the first picture. And he saw that and he got mad. He said, no, I want to use references. And so we switched back. So some people are comfortable enough using the references. I'm still not quite there yet. All right, the last gotcha for maps. This is a bug that I have not yet filed. I intend on filing it soon. If you have never used the debugging feature in LabVIEW, retain wire values, it is so helpful. It is so useful. It keeps you from having to throw probes on every possible wire on a block diagram. You just turn on retain wire values, run your code, then you start dropping probes where you think the problem might be, and you try to find it. The problem is there appears to be some sort of performance issue where if you had, let's say, an array of 100,000 elements and you turned on retain wire values and you ran your code, you're not going to see any problems. If you had the equivalent set of 100,000 elements and you turn on retain wire values and you run your code's never going to stop. Or if it does, it's going to take a really long time because there's some sort of performance issue with sets and maps in retain wire values. So I need to file a bug on that. I haven't yet done it, but keep an eye out for that. That is definitely a gotcha when using sets and maps and having to debug. All right, Norm was asking me about this before the presentation started, but I want to talk for a minute about variant attribute tables. If you are a long-time LabVIEW programmer, you have probably heard about variant attribute tables as a way to store data in LabVIEW and have fast lookups. Sounds kind of familiar, doesn't it? Sounds like what we've been talking about this whole time. So, but the variant attribute tables predate sets and maps. They've been around since LabVIEW 6.0. So in other words, forever. And what they are is a way to store metadata with really fast lookups. So it's basically a map. That's what it is. It's conceptually, variant attribute tables are a map. So if you look at the block diagram, you can see that we start off with a variant. Now, its value we never use. It's an empty variant. But there is something about variants called variant attributes, which is a way to store metadata basically as part of the variant, but not its value. It's a little weird. But what you can do is variant attributes are key value pairs. And the key is always a string, and the value gets coerced to whatever data type you want. By default, it's a variant, but as you can see, we're coercing it to a numeric here. So we've got all of these keys and values that we put in the variant attribute table. We can get the attributes based on their name. We can remove them. We can get all of the values, all the keys. So this code looks very similar to my map code that I showed before, but it's a way to use, this is how we did it before we had maps. And this was not at all LabVIEW R&D's intention for variant attributes. That is not what they added the feature to LabVIEW for. They added it as a sort of way to sort of throw some metadata on your variant, not knowing that people were just going to use it as a full-blown data store. Well, people started using it as a full-blown data store. And so back in the LabVIEW 8.x timeframe, LabVIEW R&D put in a ton of work to make these things as performant as possible, because this is how everybody was doing their maps basically back in those days. So variant attribute tables ended up being an incredibly efficient, performant way to do data lookups when you needed a map-like data structure. So the question that Norm asked before my presentation started, he didn't even know I was going to answer this, but I am. Should you ever use variant attribute tables instead of maps? That question has been asked by a lot of people since LabVIEW 2019 came out. Well, if you're in 2018 or earlier, you don't have a choice. You got to use variant attribute tables. If you're in LabVIEW 2019 or later, you should be using maps. You should no longer be using variant attribute tables, because maps are more performant in 99% of the use cases that have been tested. Now, what about the other 1%? Here's the deal. When I said LabVIEW R&D worked really hard to make variant attributes more performant, I was not kidding. They did an incredible job making variant attributes super fast lookups. In fact, they did such a good job that if your key is a string and if your value is a variant for your map, variant attribute tables end up being a tiny bit faster than the map data type. But it's only a tiny bit, and it's only for that really specific use case of key equals string and value equals variant. In all other cases, maps appear to be better. There's some technicalities about sizes of maps going back to this variant attribute thing with key is string and value variant. But for all intents and purposes, let's just say maps are always better. So let me sort of do a demo to describe some of the differences between how you might do lookups. All right. And this demo is a real world example. So this is something that I was approached with from an internal team at NI who really needed to do these lookups. So they had, this team was doing lookups, and I'm going to show the approach that they took first. The code is a little bit canned. I've got some sort of, data that they provided as sort of dummy data for the whole thing. But it's kind of weird. Their key for their lookups was a complex imaginary number. Their value for their lookups was an integer that was basically an index into an array somewhere else. So it's a key value pair where the key is a complex number and the value is an integer, okay? So this is how they were doing their lookups at first. Pretty simple, right? They've got their array of keys, which is the complex values. They do a search 1D array. Wherever it's found, they pull out the element in their array of indices and they use that. And their code was running this fast. So their lookups were 740 microseconds, give or take. And they thought that was okay, but then they heard about variant attribute tables. And so they said, hey, we've heard that these things have really good lookups, right? So what we're going to do is, remember, the variant attribute table, the key has to be a string. So they take their complex value, flat into a string, and then they associate their key. And then whenever they need to do a lookup, they take their complex value, they flatten into a string to do the lookup and grab the index. So they wrote that code, and they found that that code was way slower than the search 1D array. And so they came to me and they said, hey, we heard about this variant attribute thing. It's supposed to be all fast as the lookups, and look how slow the lookups are. What's going on here? I want my money back. Well, Remember how I said variant attribute tables are very fast when the key is a string? Well, this work that they're doing to turn their key into a string is totally what's killing their performance. Flatten into string is a very slow function, particularly when done in a loop like this. And this is killing their performance. And this is a case where they had good intentions, but once they had to conform to the variant attribute API, which is keys must be strings, that basically killed it for them. So I told them, hey, you guys are in LabVIEW 2019, right? Why not use a map? So check it out. No conversion required. The complex value is the key. The complex value is the key. That's all that's needed. And when we run this code, you guys like my icon here, a map of Texas? 13 microseconds, so way faster to do the lookups. Obviously, this code was kind of the variant attribute code was kind of messed up because it had to do those flattens, which killed everything. The better comparison here is the map lookups versus the linear 1D array search. That's the better comparison here to show why maps are so much better for doing lookups. All right, to summarize. Yes, Norm, oh, you have your hand raised. What's up?
Yep. The floating point issues, things that happen basically because no two floating point numbers are equal, right? 0 is not equal to 0.
Right.
And LabVIEW underneath the hood deals with the fact that there are, if you ask for two floating point numbers, it deals with what machine epsilon or whatever else. Do you know, it not even necessarily complex numbers, but just even using floating point numbers as a key? Have you heard if LabVIEW does any like in range of 2 epsilon kind of conversion, right? If you put two values in there that are floating points and zeros, what do you, like I said, is that the thing that you've ever asked or pondered or tested?
Ultimately, it comes down to the bits, right? You've got your floating point value. It is a certain combination of bits. The double is going to be 8 bytes worth, so 64 bits, right?
Right.
If you are doing calculations on math and then trying to find your key that way, I could see that causing a problem because then you could run into floating point issues. But if you've got like defined floating point values that are your keys and you're not doing math to calculate those, you should be fine. If there's ever any math involved to calculate the key, yes, you will run into potential floating point issues there with sets of maps, just like you would with any other API in LabVIEW when trying to do math and compare floating point values.
Well, I think LabVIEW actually does a little bit of fanciness behind the scene in terms of comparing floating points. So that was my understanding. I could be wrong. So I wasn't sure if they employed that same kind of extra fanciness when comparing floating points.
My understanding is the checking of a floating point to see if it is in a map or a set is going to be the same as any other comparison in LabVIEW. That's my understanding. Derek, you have your hand raised as well.
Yeah, so just a quick tip of something I do for code readability when using maps is you can set the key and the value labels. And then in your loops, when you are accessing them, you can unbundle by name and just get a little bit more meaning.
Okay. Yeah. So just to illustrate what Ben was talking, or what Derek was talking about there, whenever you've got a map and you do the trick that I was talking about, where you can iterate on the elements of the map, Derek is saying, why not throw some labels on these guys here and use unbundle by name instead? That'll make your code a little bit more readable. And I think that's a great suggestion. To summarize, you will use strings when you need to do pattern matching, like with the match pattern function or the match regular expression function. If you need human readable values on a front panel on a block diagram, if you need to trigger a case structure, those are all reasons you might use strings. For arrays, you will use those if you need to do index-based lookups, if you need to support unsorted data, if you're doing math and you're using APIs that already take numeric arrays. You want to use sets if you want ordered data with fast lookups. You want to use maps if you have key value pairs and you need fast lookups and you're in LabVIEW 2019 or later. I have a couple more minutes here. Does anybody have any questions about everything I just threw at y'all? Norm.
I'll defer if anybody else pops up, but I do have one comment, I guess, to make on arrays with regards to speed.
Go for it.
Okay, seeing when working on arrays, you can do these bulk operations where you basically can like add an array to an array and do things of that nature. There are cases where actually indexing, like dropping the for loop and doing it for every iteration of the array can be faster when you're doing stuff in terms of math and analysis and index based, not necessarily as much of lookups, but just doing operations on the arrays themselves, because LabVIEW, depending on the size, we're going to be doing some challenges. We might have a lot of data flying around. In one case, it's a lot of operations of a very small memory chunk, and the other one, it's a very large, or it's a single operation on a very large memory chunk. And then there's a little bit of a pivoting on terms of like, when is one going to be more advantageous within LabVIEW, the way that it does stuff. So just keep an eye out when you're working with arrays. You can do bulk operations, which are really, really nice, where you just shove whole arrays into things. And then occasionally, depending on how much speed you're really trying to eke out, you can do better if you index out one element at array and let LabVIEW maybe do some fanciness behind the scenes to figure out stuff faster.
That is something that's fun to experiment with. Sometimes you might have the add function and have two arrays going into it. And you might say, hey, what happens if I wrap this in a for loop and make it a parallel for loop? Does that make things faster? Sometimes it does, sometimes it doesn't. So if you're trying to squeeze out performance, definitely those type of fun experiments are something if you have time to give a try to. All right, you guys. Well, that is all the time I have. Thanks everybody for coming. I appreciate it, and we look forward to seeing Norm's presentation next week.
Well done, ending on time even, as always.